For the second part of this lecture, we're going to talk about optimization of neural networks. And by that, I mean, how do we really find the optimal parameter vector? So you've roughly seen the main idea behind every algorithm we're going to talk about, gradient descent based algorithms, but there are a lot of different algorithms which sort of fit into this general mold, and little tweaks and things that we can do to it which make it much better. One thing in particular that we're not going to talk about today or in this class really is second order methods. Like I think I've alluded to these before. So, okay, sorry, let me maybe make a bit clearer what the distinction between first order versus second order methods is. So first order methods, these are things which only use the first derivative. And by that I mean the gradient in multivariate settings. So things that only use really the first order method, first derivative, or first order method, and naturally you can guess what second order methods are. Yeah, I'm not even gonna write this all out. This uses the second derivative. Now, first order methods are typically preferred. Why is that? Because first order methods, they don't require as much computation. They're much faster. They're much simpler often. So you can do a bunch of steps very quickly and cheaply. Whereas second order methods, they typically require you to compute things like the Hessian, which is a much harder thing to do because it's now going to be, it's going to be much more higher dimensional, and this will allow you to take fewer steps, but the thing is each step will become a lot more costly with a second order method. That's kind of the trade-off when you're looking at this, where you can either do a lot of cheap steps or a few more expensive steps. And the question is how many or how cheap they are and stuff like that. That really factors into which one you choose to use. In general, it seems like first order methods are winning out, and second order methods are relatively less popular. But yeah, in general, first order methods are what you would go with, and so that's what we're going to focus on. But second order methods are an interesting topic as well, and yeah, if you're curious, you should look into it more. But like I've said, the main thing that we use when optimizing neural networks is something known as gradient descent. And okay, literally we do not use gradient descent, but we use gradient descent style algorithms. So the most vanilla form of gradient descent is often called batch gradient descent. And what is it? Well, we just do the following update repeatedly. We say theta becomes theta minus some learning rate times 1 over n, summation of the gradient of theta, L of xi, yi, and theta. So this should look pretty familiar to you. You just compute the gradient average over the training data set, and you take a step in that direction where it's decided by some step size eta. And this is a hyperparameter. So this is the most classic style of gradient descent, and it generally works well in the sense that it's accurate. Now, the reason why it doesn't work super well is because of this summation here. This pesky summation has n terms in it, typically, where you have to average the gradient over the entire training data set, and therefore that's going to take a long time if your n is very, very large. And this is kind of a waste of time in the sense that maybe you don't really need to look at all your data to get a good estimate of the gradient. Like, why are we doing this? The reason why we do this is this is kind of like an empirical estimate of the true gradient of the function. It's trying to estimate the random variable. Like ideally what we would do is be able to plug in here, instead of this right here, we'd like to plug in the gradient with respect to theta of the loss function of x, y, theta, and kind of the expectation of this when x comma y is drawn according to whatever distribution your data is drawn from. This is ideally what we'd like to plug in, but instead we have to plug in this sort of empirical average. It's just sort of we're trying to estimate this average. Now, this is great because it'll get us a very good estimate of it. But the thing is, maybe this is more accurate than we need, in the sense that because we're just taking a tiny little step, maybe it's okay if our estimate of this true gradient is not exactly a perfect estimate. Maybe we can afford to do with a little bit of noise. It'll be less accurate in terms of how close this is to this quantity right here, but this decreased accuracy comes at the benefit of that is much faster to train. And so that's where stochastic gradient descent comes in. So like in its purest form, stochastic gradient descent, let me just write stochastic GD. In its purest form, this is just going to be when we pick a single point and update it based on that. So theta becomes theta minus eta times just this. So this is stochastic gradient descent, where you can see the difference from before. Instead of averaging over the entire data set, now we just pick one and take a step based on that. Now the question is, how do we pick one? Well, there's many ways. One way is we can just pick uniformly at random each time, but maybe more common is that you randomly permute your data set and then you go over it one point at a time and just do it in a random order, updating the parameter vector based on the gradients of each point. So that's maybe a bit more common in practice to do this iterating over it in order rather than just picking things uniformly at random, though we would still do some data shuffling after each epoch. And I guess I should clarify perhaps what an epoch is. An epoch would be when you go over your entire training data set once. So what you do is basically shuffle all points from 1 to n, and then you iterate over your entire data set in one go, and that's one epoch. Then you reshuffle your data set, and then you go over it again and again and again. So yeah, this is stochastic gradient descent, and you can see we kind of took the other end of the spectrum, where now we're going to get only a very, very poor estimate of the expectation. Like each individual one might be pretty poor, and it only really averages out after we do several steps. So the middle ground, which I kind of mentioned earlier, is called MiniBatch SDG. This is the most common algorithm used to train, and it's kind of what people refer to when they say SGD. It's sort of implicit that this is over a mini batch. And again, what we do is very similar to before, but again, it uses a middle ground where we have here, now we average over just some batch, the mini batch of this loss function xi, yi, theta. So yeah, we would typically choose, so you can see we have these sets here where B is a set. So what you can think of doing is, suppose you have all your data set, your data set all lined up, x1, x2, x3, ... all the way up to xn. And what you might do is just like split it up into little batches and then break it up, and then eventually, and you just iterate over these in order. So it's kind of like the middle ground, where instead of shuffling your data and then iterating over them one by one, well, now you split it up into little batches of size b, or size magnitude of b. And how big do we typically choose these? Well, it's common to choose, say, size of b to be equal to, say, 64 to 256. Something like those. Those are reasonable batch sizes. But you can see it's much bigger than 1, so it gives a chance to get a better estimate of this the expected gradient, which is what we're trying to optimally do. But it's much, much faster than saying taking size of b to be n, which is what we would do for just standard batch gradient descent. So yeah, it gets a coarse estimate of this, which is better than before. And this is pretty good. So these are the main primary methods of training a neural network, or I guess this is the most common one. But there's some drawbacks with kind of all of these methods that we've talked about. And what are these challenges? Well, there's a few. For example, how do we pick? Well, let me just write it like this: eta. Well, how do we pick eta? As you might have seen before, if you choose eta to be very, very small, then you run into the issue that you make very slow progress and you don't converge to a point with any reasonable amount of time. On the other hand, if you choose eta to be very, very large, then you might just overshoot the optimum, and yeah, you won't get close to a good optimum. So you need to somehow choose a balanced eta, which is neither too small nor too big. Another thing is maybe one way to do this is using learning rate schedules, so LR schedules. Now, the downside of learning rate schedules, what is a learning rate schedule? Is maybe when you say, okay, we're going to start with some learning rate and then maybe decrease it over time so that maybe it can handle the case where eta is too large, and then if you don't like it, then it'll eventually become smaller, and yeah, it'll eventually become smaller, and then you'll be able to take smaller steps and eventually convert to an optimum. So like learning rate schedules is an approach that's sometimes taken, but the problem is with learning rate schedules is that every data set is different, and a learning rate schedule in the naive way is not data dependent. So in other words, there really should be no one size fits all learning rate schedule. So let me just say that a downside here is that this doesn't adapt to the data. And another thing here that you'll notice is that this kind of, okay, I wrote dot, but make sure you understand that this is just a scalar multiple. There's no dot products here. Sorry, I just realized I'm missing a gradient sign here. So the one thing you'll notice here is the fact that you apply the same learning rate, the same scaling of the gradient to each coordinate. However, it might be the case that certain coordinates are maybe faster or slower than other things, and maybe you need different learning rates for different coordinates. Well, how do you figure that out? Well, it would be harder to tune these as hyperparameters just because you're making your life even harder. But so the kind of question here is, can we have different eta for different coordinates? So these are some of the main challenges that we face when we're trying to do use an optimizer, and some of the reasons why it's not going to be super easy, and then why you might run into issues using, say, MiniBatch SDG. So to address these, there's a number of different optimizers which have been proposed. There's like hundreds of them probably, but there's a few which seem to have withstood the test of time, and they're ones you really should know if you're doing any sort of work in modern deep learning. So I'll try to communicate some of the optimizers which people use a lot in practice. Yeah, they're still first order methods, but they're going to have a few more tweaks over MiniBatch SDG, which will cause them to become better in many cases. And the first one I will mention is something known as momentum. I don't know why I have quotes, but I put quotes because maybe it's trying to imitate the idea of momentum in real life, in the sense that you can imagine you have a ball rolling down a hill. Well, if it's already moving fast in a direction, well, it'll keep moving fast in that direction, even if the shape of the hill changes over time. So yeah, that's kind of the idea behind momentum. And let's take a look at this picture, which tries to illustrate what's going on here with momentum. So we'll describe formally what momentum is in a sec, but this is the kind of image you can see here, where this is a loss function. So these are contour lines. The value of the loss function on one of these lines is going to be equal. So essentially you can picture this as a valley where these ovals are kind of contours which I guess are equal level. So this is kind of at the top and this is the bottom of the valley. So the idea is there's some details which are not shown in this picture, but essentially this black line, the black line here, that is the gradient at each point. So you can see here, if we're at this point, then what the gradient would tell us to do is to go in this direction. So let me do something in, yeah, let me just do this. So you can see the gradient, if we were to do gradient descent starting from here, then it would tell us to go this direction, which is almost perpendicular to the direction we want to go. And the gradient isn't marked at this point, but you can see over here it would probably be something like this. So yeah, it would kind of go basically the opposite direction, but very almost 90 degrees compared to the direction we want to go. And going another step would maybe be over here and then over here. And maybe you can see where this is going. The idea is that if we do SGD, then maybe it would take a bunch of steps which are pretty much orthogonal to the direction we want to go. But the reason why this is silly is because if you really think about the steps that we would be taking like this, where we're going like, let me do it in a different color, we're going this way and then this way and then this way and then this way. Well, you would notice over time that we're making progress in this direction. Slowly but surely, that's the sort of way that we're going in, if you average over many steps. And in fact, that's what momentum tries to capture. You can see that this red line, the red is momentum. Momentum plus SGD, like SGD plus momentum, I guess is how it might be called. Yeah, you can see that while it originally starts going in the same direction as the gradient, over time it learns the fact that, okay, we're over this trend, we're kind of going in this direction, so we're going to preserve a component of our gradient and eventually start going this way. So that's the idea behind momentum. Use the fact that you were going in a direction in previous steps to tell you that you should keep going in that direction. So let's maybe be a bit more precise as to what momentum is. So momentum is going to be, we're going to have another parameter. So what we're going to try to do is say theta becomes theta. So before this would have been like minus eta times the gradient or whatever. But yeah, but let's leave this blank for now. And what we're going to do is we're going to define kind of v of t, which can be seen as the velocity. And let's write it as follows. So it's going to be some new hyperparameter gamma times v sub t minus 1 and plus 1 minus gamma. And then this will be our gradient computation as we had before. So yeah, this is essentially the gradient calculation. And for some times in the future, I'm going to just succinctly refer to this gradient at time t as g sub t, just because it's a bit of a mouthful to write this out every time. It's going to be pretty much the same thing that we're going to use a lot. But yeah, we just compute the sort of averaged gradient over a mini batch, and then that becomes gt. And you can see here what we did is we take the velocity. You can picture this as being the velocity of the of how we're moving to be a weighted average of the old velocity plus something times the gradient itself. So we're typically going to choose gamma. Well, we're definitely going to choose gamma to be less than or equal to 1, or probably less than 1. And say gamma equals 0.9 could be okay. But it's just an example parameter. There might be different things for different settings. But the point here is that if you plug that in, you can see that this new velocity is going to be 90% times the old velocity plus 10% times the actual new gradient. So this we just updated by subtracting out the velocity, which includes this which includes both the old velocity rescaled and then the gradient update, but only fractionally so. So yeah, hopefully you kind of get the idea of where the name momentum comes from. You essentially keep the previous velocity and build onto it, though it decays, and instead you weigh in some of the gradient at the new point. Okay, so that's momentum. Try to think and see if you can figure out why this corresponds to the type of picture I drew here. If you can connect those two, that's great. Okay, let me note one more thing which will be useful a bit later. Let's see if we can unroll this expression for v sub t. Well, this can be written as, say, 0.1 times... Okay, I'm going to also leave out this eta, but it can be written as basically this, 0.1 times g sub t, plus then we have 0.1 times 0.9 times g sub t minus 1. And where did we get that from? Well, I just took this term here and I plugged in the same expression sort of recursively, and we get the next term. And then we have, say, 0.1 times 0.9 squared times g sub t minus 2. And you can see where this is going, plus dot dot dot. And then eventually we're going to get down to something like 0.1 times 0.9 to the t minus 1 times g sub 1. So you can see it's one way to view this is it's a weighted average of all the past gradients. So you can see that the greatest weight is placed on the most recent gradient, but it's also going to include something of the previous gradient and then something smaller of the previous gradient all the way back to the original. So that's one way of seeing the updates that we make as a weighted average of the past. The other thing I'll note is the fact is what are these total coefficients here? Like what are the total weights here? If you add up 0.1 plus 0.1 times 0.9 plus 0.1 times 0.9 squared, well, you should remember your geometric series. And if you do this, if you add up these coefficients, you get the total coefficients. That's going to be 1 minus gamma to the t, which is approximately equal to 1 when t large. So this is going to be important later, but the point is you can see that we'll revisit why I did this calculation a bit later. But for now, you can just see this as as some sort of, there's going to be some sort of coefficients, and in the end, it's going to, as t gets large enough, then it's just basically going to be a weighted sum which adds up to 1. Okay, so that's momentum, and this is very important. Like, in fact, SGD plus momentum is kind of the state-of-the-art optimizer for many cases. We're going to talk about more sophisticated things, which can be better in other places, but generally momentum is pretty good already. I'll mention now something which is also used, especially, and can be more efficient on, say, convex problems, not neural networks, but I'll mention it just because it's interesting and a little bit mysterious. So there's something called Nesterov momentum, or Nesterov's accelerated gradient. And it's rather similar to what we had here. So let me even just copy and paste it. It's pretty much the same thing as we had right here. There we go. The main difference, or really the only difference, is the fact that instead of computing, we kind of take a half step and then we do the computation. So let me just show you here. Essentially, instead of computing the gradient at the point which we're at, what instead you do is you sort of take a half step based on what the old momentum was. So you just do this. And then you compute the gradient at this new point. So you can view each sort of step here as being, first you do a half step, which is kind of, you update your parameter to be based on the old velocity, and then you compute the gradient there, and then you compute the true new velocity, which gives you the new point. So yeah, this is Nesterov momentum, which is, again, it seems a little bit arcane. It can be better in some cases, but I think it's neat just because of the fact that this can improve it by sort of taking looking at the midpoint midpoint in a certain sense. So yeah, that's not too much used in deep learning, but it can be better sometimes. But yeah, the more important one is Nesterov, is just not regular momentum, not a Nesterov momentum. Okay, so this is how we deal with some of the issues, and in particular, you can see this very clear example as to why momentum can help, because it'll kind of deal with these cases, especially when we're dealing with ill-conditioned, say, gradients. But there's still the big challenge which comes up, which is how to pick this learning rate. And instead, one way of overcoming this is something known as adaptive methods. So adaptive learning rates are kind of what this family of algorithms are called. And yeah, like why are these called adaptive? It's because we change eta. Oh, let's just say change the learning rate over the algorithm. And importantly, we can change it based on how fast different coordinates are moving. So maybe, yeah, let's say based on, I'll use the quotes here because it's not quite precise, importance of each parameter. So for example, if we have a lot of updates, what do I mean by that? Like imagine each step we're taking, each time we compute a gradient, we take a step and we take a step and we take a step. We're moving sort of very fast in one coordinate or one parameter. Then what we might want to do is we want a low learning rate. On the other hand, if they're very occasional, maybe we take very infrequent steps in a certain parameter, or perhaps they're very small steps when we do take them, then we'd want to make the learning rate be larger, just so that we really take advantage when something happens. And this can be especially useful when we have, say, sparsity. That is, we have maybe data or gradients which might have different properties for the different coordinates, in the sense that some might be 0 a lot, whereas some are going to be non-zero and stuff like that. So yeah, this can often help in sparse settings. And I'm just going to remind you that we've been using the notation that GT, which is a sort of R to the p dimensional vector, one for each parameter. This is the gradient at time t. Cool. So the main idea is that we're going to, I guess let me say it this way. The update that we've been doing so far, let's break it up based on which coordinate. So theta of t at time t plus 1 in coordinate I is going to equal to theta t I minus eta times g sub t I. So yeah, this is the coordinate I update. And this is just basic gradient descent, however we do it, either gradient descent, SGD, or MiniBatch SDG. They can all be written like this for now. What we're going to do is use the intuition that if there are, like I was saying, the intuition was that if you have a lot of updates or many big updates, then we're going to want a low learning rate for that parameter. So what we're going to do is we're going to slow down the learning rate for a coordinate if we see a lot of updates on it. So let's define g sub t comma I. yeah, we're going to essentially accumulate the squares of the gradients for that coordinate from time 1 to the present time. So if this is very small, if these are small, then GTI would be small. If we've had big or many updates, then this would be a rather large quantity. So this kind of G sub T comma I quantifies how many updates we've seen, or how the sort of magnitude of the updates we've seen in coordinate I up to time T so far. So this quantity here, it's the sum of some of the squared gradient updates per coordinate. So now with this in place, we're going to have a just a minor tweak to this previous classic SGD algorithm. Instead, what we're going to do is we're just going to do the following. We're just going to do a rescaling of the learning rate as follows. It's a bit cleaner. So this is the update. This is all we do. You can see it's very similar to the previous SGD update. So this is what is known as, oh yeah, let me tell you what this is called. This is called ADAGRAD, which kind of means adaptive gradient descent. This is a common optimizer and you should know it. So you can see that it takes the old type of updates, but instead what it does is it scales the learning rate based on how many updates we've seen in the past. So again, if these G sub T I, if we've been seeing a lot of updates or a lot of big updates, then we scale down the learning rate. So we slow down because otherwise we'll overstep. And if we haven't been seeing many, then it'll keep that learning rate large and it'll keep going. And similar to before in previous part of this lecture, this is going to be, say, some small number just to prevent dividing by things like 0. And then maybe you can choose this epsilon to be something like 10 to the negative 8 or something, just to prevent these divisions by 0. So yeah, this is ADAGRAD, and it will figure out which coordinates or which parameters need more updates versus fewer updates as time goes on. So this is good, and it has strong theoretical properties. The reason why we have perhaps an issue with this approach is the fact that, think about what happens as the time t goes to infinity. Notice that notice the fact that this will just keep growing bigger and bigger. G sub ti, as t increases, this will just become bigger and bigger for whatever coordinate it is, and that'll kill the learning rate. It'll become smaller and smaller, and over time, eventually, this is going to just, it's just going to shrink, and we're eventually going to reach tiny learning rates where we can't make any progress over time. So this could be okay if we have, say, a high enough learning rate to start with, or maybe we transition and get to the optimal point fast enough. But there's some chance that we're just going to not make it there because our learning rate died too fast. And that's just because that's just how it goes. So yeah, the idea that we want to get here is the fact that maybe we're being too harsh in terms of our penalization of the learning rate, and by remembering the entire squared gradients for this coordinate, then we're being a bit harsh on it. So instead, what we're going to do is we're going to instead keep a weighted sum which remembers the more recent updates, so that it can still do something like this. If it keeps the kind of recent memory of what it's done, then it can have the same behavior, but it'll forget very old things. And the reason we want to forget old things is so that we don't end up with this becoming too large over time. So yeah, there's some sort of memory here, and maybe this is familiar to an idea you've seen already in this lecture. Think about it for a sec. Where have we seen a case where instead of taking just an aggregate of things, we instead use some memory, some weighted sum of things? Well, if you thought momentum, then you're totally right. You can see that, like I said, this is going to be a weighted sum of the gradients. Now, essentially, all we do is instead of doing a weighted sum of the gradients, what we do instead is we do a weighted sum of these squared gradients. And this is something known as RMS Prop. So what we do here is we're just going to do a kind of weighted sum as we did before, where we have g sub t sub I equals, say, something like, I'm just going to write 0.9 in, but you could also change this later. And this is going to be a weighted sum of this plus and let me just to draw a comparison with momentum, let me just sort of copy paste this so you can see it next to each other, just for the time being. You can perhaps see the similarities between these two terms. You just take you take the current parameter and you set it equal to, the new parameter you compute is going to equal a weighted sum, which places a lot of weight maybe on the old version of the parameter, and then a smaller amount of weight on some new parameters. So this, recall, is going to be gt, and yeah, you go from there. So this is very similar, except you just work in, the only difference is that you work with the first moment of the gradient, that is just the gradient itself here, whereas here you're going to work with the gradient squared. But otherwise, it's the exact same idea, which is quite nice and I think a bit elegant. So yeah, let me just write that. Momentum, but on the second moment of gradient, that is gradient squared, rather than first moment. And then the update rule is, once you've got that in place, where you're just doing these updates to this g sub t comma I in this way, then the update rule is essentially the exact same as attograd, where you do t plus 1 I. Right, so this is the exact same thing as we had for attograd. It's literally the same expression right here, but the only difference is the fact that this g sub t, this now has this weighted decaying sum that we have here, similar to momentum. That's the only difference. So, okay, we've seen a lot of different things. We're going to present one last optimizer, which is kind of one of the most popular ones that exists right now. And it kind of combines the two final ideas we've seen together. So there's two main ideas that are sort of key to our discussion so far. One is the idea of momentum, where if you're going in a direction, then maybe you want to keep going in that direction. And the other key idea is that of how to figure out the learning rate. You kind of take the learning rate and then you rescale it based on whether you've seen big or small steps in that coordinate. Those are the two things. So why not just do them both at the same time? And this has a very elegant interpretation. It's kind of like you're doing a weighted average on both the first and the second moment at the same time. So this is one of the most popular optimizers, like I said, and it is known as Atom, which is, I guess, a kind of cute name, but it's just Atom. So, like I said, it's momentum plus RMS prop at the same time, and then there's also an additional plus some bias correction, which we'll see in a second. So all you do here is just essentially do these updates as I described. So let's define beta 1, beta 2 to be hyperparameters. And what we're going to do is denote two things. So mt sub I. This is m stands here for mean, and this can be written as follows. So this right here is going to be the momentum component. And the other component is going to be the variance. So I'm using v here. Don't get this confused with the v we used previously for velocity. This means here variance, even though it's not quite the variance, they still refer to it as v. The reason it's not quite the variance is because we don't do recentering of the when computing this. But anyway, v sub 2. And this is kind of roughly the RMS prop. Updates. And this is kind of like you can see here, it's essentially the same thing we did here, except we used a parameter instead of 0.9. I just wrote that for simplicity. So yeah, you essentially track the first moment and the second moment of the gradients at the same time. And what do I mean by this bias correction? Well, this is just a throwback to what we talked about here, where you remember I said that you have the sum of these coefficients, which is going to be 1 minus gamma to the t, which is approximately equal to 1 when it's large. But it turns out that it can kind of make it a little bit better if you do something smart when it's small, and that's kind of a rescaling. So let's just write that here. What you'll do next is m at t comma I, which is equal to m t comma I divided by beta 1 to the t, and v hat is just the same thing, except with the different parameter. And the idea is these account for the fact that at every time step we have we would have a weighted sum of things which doesn't quite add up to 1. So this sort of rescales it so that the coefficients total would sum to 1. It makes it so that we have an appropriately with these parameters are of the appropriate magnitude as we proceed. Okay, and then once you've set up all these parameters, it might seem a bit odd, but really it's nothing too complicated. You understood momentum, hopefully you understood RMS prop, and just put them both together and get something like this. So yeah, this is the final update rule that you have, which again looks very similar to what we had for RMS prop in terms of putting this in the denominator here, and momentum because you update based on the weighted sum of the previous gradients. And so that's essentially one iteration of the algorithm, and you just run these steps again and again, and if you keep doing these updates, then you get a pretty good answer. Now, one thing to note is the fact that we've kind of, why did we do all this? What was the purpose of this? Well, the purpose of all this was in order to make it so that we didn't really have to be so careful about how we chose eta. This eta is a really tricky parameter which can vary a lot based on different data sets, which eta is good. But we wanted to skip trying to tune that so that it kind of figures out what's a good eta by itself. So now we we kind of got rid of the need to tune eta, but none, or at least to some degree, in the sense that maybe we have eta equals 1 versus eta equals 10, but over time it'll figure out which is too big or too small and sort of rescale it appropriately. But the thing is, we got rid of some of our need to tune eta, but instead we introduced 2 new hyperparameters, right? So we're kind of just introducing more hyperparameters to get rid of other hyperparameters. It seems like we've just kind of made our job, we haven't really made the problem any easier, right? But the perhaps surprising thing is the fact that there are good values for these hyperparameters and we don't typically need to tune them. That is, often we take beta 1 to be equal to 0.9, beta 2 to be equal to 0.999, and epsilon to be 10 to the minus 8. This is just what we got here. So yeah, this is a common setting of parameters for Atom. It's kind of what are recommended as the default. And you might be thinking, why are these good settings for these parameters? Well, nobody really knows. These just kind of work. This is a little bit of the black magic which comes up in deep learning. These are just good values. So I don't know. You can play around with them. You can try changing them, but these are somehow the ones that people have agreed on are good parameter values. So yeah, like I said, out of the box, Atom is kind of the go-to optimizer in deep learning. And if there's any model that you have, just throw Atom at it, and it generally works pretty good, pretty well. However, this is not necessarily always state-of-the-art, in the sense that in many cases, SGD plus momentum, if you appropriately tune the learning rate in the right way, then sometimes that can get state-of-the-art performance. So yeah, you kind of have to think and be a bit careful about what works best. Yeah, but that's pretty much all I want to say about optimizers. Yeah, so these are all things that should be in your arsenal whenever you're thinking about optimizing a neural network. These are all common, and people will expect that you're familiar with all of them. So be sure you understand them all.